Okay, 11.2, infinite series. So more or less we're taking a sequence here, and instead of one, a sequence of numbers separated by commas, we're going to instead kind of add these numbers up in a sense. So that's the short answer, but there's more to it than that, of course. So let's look at Zeno's paradox. So if I want to walk to the door, I can never actually do that because I have to walk I have to walk, 1 meter, right? I have to get halfway there. And then I have to get half of the remaining distance there. And then half of the remaining distance. Oops. And then half of the remaining distance, and so on and so forth. So I have an infinity of things to do. No human being can ever do that. So I'm never going to be able to leave this room, which is unfortunate. So of course, we can get around this difficulty, of course, but because we're going to know that this is going to add up to, well, 2, hopefully. But anyways, this is all just to introduce what is a series. So this is called a kind of an infinite sum here. We call that an infinite series, or just a series. Okay, in general, we have something like, a1 plus a2 plus a3 plus a4 plus whatever, which we can summarize quickly with the notation n equals 1 to infinity of a n. So we call this a series, of real numbers. Okay, we're going to insist that a n is a real number for all n. So Zeno's series is 1 plus a half plus a quarter plus dot dot dot. Okay, we can write this as summation n equals 1 to infinity. Now, what do we have happening here? We have, oops. So this is a half to the power of 0 plus a half to the power of 1 plus a half squared, and so on and so forth. So in general, it's a half to the n. Oh, wait a second. It's not quite right. Okay, this is the oops, change our color here. This is the n equals 1 term, right? So when n is 1, we get a 0 up top there. So we're going to have to adjust a little bit and put, oh boy, put n minus 1 as our exponent. Okay, so next thing I want to talk about is, okay, what we mean when we say that an infinite series actually, adds up to some real number. So we're going to say, when an infinite series converges, like what do we mean when we say that? So we're going to need some definitions first. So if we have an infinite series, summation an, if this is a series, then the sequence, I'm going to define a sequence attached to this series. So we'll say S1 is equal to A1, S2 is equal to A1 plus A2, S3 is equal to A1 plus A2 plus A3. So S lowercase s n is equal to summation I equals 1 summation I equals 1 up to n of a I. Why don't I use a lowercase n instead of the I? Sorry. You can tell these videos are just like my lectures. Lots of little changes being made as we go. So this is a sequence, S1, S2, S3, S4. So we call this the sequence of partial sums. For our original series, sigma an. So it's a sequence, S1, comma S2, comma S3, comma S4. This is a sequence. So it's a little, and it's a sequence of partial sums because, well, I hope it's more or less self-explanatory. Okay, S1 is the sum of just the first term. S2 is the sum of the first two terms. S3 is the sum of the first three terms. S16 is the sum of the first 16 terms, and so on and so forth. Okay, one thing before I close the video. You'll notice up here, I did not put any, seems to be missing something, right? Okay, well that's a common short form, which I will use, and I believe the textbook does too. Okay, so if I write sigma without any kind of anything below or above, okay, what I mean is summation n equals 1 to infinity. So yeah, it's a short form because, very often series are going from 1 to infinity, so especially in our textbook. So I'm going to use the short form. Okay, see you in the next video.